Okay, uh, next question here. The diagram shows a velocity time graph of a car, at which point is the car decelerating most quickly. So a couple things about this question. First of all, when we use this term decelerating, really what we're talking about is negative acceleration. Now, really, there's only one concept here, and that's acceleration. But oftentimes when we're talking about a negative acceleration, sometimes people will use the word deceleration. Even though we prefer to talk about acceleration, and this question probably should have said, at which point, does the car have the greatest negative acceleration? And that would have actually been a little bit more exact. But in the world of, kind of non-physicists, we can use that term decelerating. So just something to kind of note. Okay, so when does, this car have its biggest negative acceleration, right? So when does it have the biggest negative number? Or in other words, when is it decelerating most quickly? So we have to think about what we're given here. And this is really the crux of this problem, and this is why I picked this problem to kind of go over. So we have a velocity time graph. So at every point along this curve, it's not representing a position. It's representing a velocity. Okay, this is very, very different than probably what you're used to, right? Almost all of the time, when we're graphing X and Y, we're thinking of positions, in space, in two-dimensional space. And in this case, we're not thinking of position at all. We're thinking of time and velocity. There's no position really here at all. Yes, position in some ways is baked into velocity, but yeah, we really are looking at velocities here. So what we need to, when we look at these points, right, A, B, C, and D, and we're trying to decide which of these has the biggest negative acceleration, we need to think about what we're given here, velocity and time, and what we're looking for, acceleration. And in this way, we can actually even use, guess. And it's going to be a little bit different. We really only need the goo part of guess. And here it's let's switch up the colors a bit. We're looking for, we're given velocity and we're given a time, right? And we want to know, well, what is acceleration? And the reason I didn't write any numbers here is because we're going to be, at point A, we would put in, our numbers for point A. At point B, we could put in our numbers, right? And so on and so forth. And we could do it at point C and we could do it at point D. And what's our equation? Well, if we looked into our equation sheet, acceleration is velocity over time. Okay. And kind of going in, if you watched my video about the Durong station average speed question, we also kind of have this acceleration average is, our change in velocity over our change in time. And if you didn't watch that video, please go watch it. The short kind of explanation here is this symbol, delta, this triangle, just means change in. Okay. So our average acceleration is our change in velocity divided by our change in time. And this is going to be the, kind of our biggest clue to solving these graph questions, is we know when we're talking about a change in, again, this is from another video, V2 minus V1 over T2 minus T1. Now, what does this look like? this should look very, very familiar, right? This looks like y2 minus y1 over x2 minus x1, right? All I've done here is, instead of writing x, I've written t, right? And instead of writing y, I have a v. So this is, right, slope. That's slope. It's the slope of this curve, right? Instead of y, I have v. Instead of x, I have t. So instead of having y2 minus y1 over x2 minus x1, which we know is our definition of slope, we have v2 minus v1 divided by t2 minus t1. So now we kind of have the biggest, insight here, the biggest clue into doing this question is that we're really looking for slope. We're looking for the slope of this curve at a particular point, right? And this is where I do have to kind of, wave the magic wand a little bit, because we haven't got to calculus yet, and you won't get there till probably, your senior year. But how can we have a change in anything at a single point? How can there be a change? And there can't be. There can't be a change because it's a single point. But it turns out, through math, that, what if, instead of trying to get the change, in a single point, we looked at, the difference between A here, and we went, let's say 0.1 seconds. We went like a really small amount of time. And so then we would get here, I can't really zoom in any further, but we might get, A, plus 0.1, right? So we moved a little bit, but really, is like 0.1 the smallest number we can get to? No, right? Like, why not just why not 0.0001? Or, why not 0.000000, and just keep adding zeros, right? We could add zeros, on until infinity, really. And that point, at a certain, if I added enough zeros, we would be so close to point A that we really couldn't tell the difference between A and that new point. Even though, there would be an actual point, it would be so close that there would really be no difference at all. And that is our change in here. Okay. So it turns out that in the case of a curve like this, if we do those very, 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 very small changes, and let me get my eraser out here, so we're kind of cleaning this up. It turns out that, oops, I did not realize it would erase my curve here. That's fine. Just be a little bit more cautious with this erasing. And sorry, I was saying, it turns out that if we, do these very, very small changes, right? It turns out that the slope that we're talking about, let me fill this curve in. It turns out the slope we're talking about is if you drew a line that doesn't, that just barely touches the curve at that point. Okay. Right? Or if you drew a line that just barely touches the curve at point B. Or if you just barely drew a line that just kind of comes in and just touches that curve at that one particular, oops. Let's try to draw a bit straighter. There you go, like this. Or at point D, if you drew a line that just kind of comes in and barely, barely grazes the curve. These are the slopes of these lines is what we're talking about when we talk change in. Okay, so what we are then looking at is for point A, right? We're kind of looking at the slope or steepness of this graph, if you will. You know, and perhaps this is a bit of an easier way to understand it is the steepness of this hill, right? It's pretty steep, right? If you thought of this as a hill you were walking up, you know, the steepness is this line, right? Is represented by this line, and if it just continued at that steepness, you know, that hill would look differently. It would look like this line. But as you go up this hill, you know, it gets more steep. B is, you know, at point B, it's steeper, right? That steepness might look like that, right? So here we have, you know, if we have upwards steepness in a velocity time graph, we have positive acceleration. Here at C, it's pretty flat, right? If you were standing on the hill at this point, you wouldn't say it was steep at all. And so, you know, this line here, right? If I asked you the slope of this line, you would tell me 0. That it has no slope. It's completely flat. And then finally here, what we should be able to see is as we're going down the hill, right? The steepness is actually, you know, negative. And so our answer here must be D. It's actually the only place on this hill where we have negative acceleration. And therefore, you know, of these 4 points, point D is where the car is decelerating most quickly.